third and final talk for the day. Frank Ferro, who is the Senior Director of Product Management at Rambus, will be giving our closing talk today. Frank has had more than 20 years of experience at companies such as AT&T and Lucent, with extensive experience in the wireless communication segment. Nowadays, he leverages his background to deliver cutting-edge memory interface solutions for multiple verticals, including AI and machine learning. Today, Frank will guide us through Rambus's distinctive approach on memory interfaces for high bandwidth silicon. Frank, so whenever you're ready, just like pop on your camera and yeah, you can start sharing.
Hey, Akash, thank you for the nice introduction.
Oh, it was easy to go.
Okay. All right.
You have so many positives.
Okay, great. Well, again, thank you everyone for joining into my presentation. I'm going to spend some time, the next 20 minutes or so, talking about advanced memory solutions for AI, ML, specifically focusing on the training aspect and looking at some of the memory solutions that are available to support training. So this is always a good place to start. Clearly, the exponential growth in data is driving everything we do throughout the whole ecosystem in both the semiconductor and the high-tech industry. So right now, the data is driving change across from all the way from up to the cloud infrastructure, through the edge of the network, and then even down to the endpoints. So we've got to deal with a lot of data. It's putting stress on the existing compute architectures for sure. So we need more and more compute power, which has been good, and compute power has been growing nicely. But then we're finding that even though the compute power is growing, the memory bandwidth has to kind of grow in lockstep with that. And sometimes those things get out of phase, and we're in a phase now where the compute power is growing, but the memory bandwidth is struggling to keep up. So that's given rise to a number of new types of memory solutions, and we're going to look at those shortly. If you look at the right side of this picture, you can see how neural networks are now being used to solve some of these data problems. It's kind of a self-feeding thing where neural networks have been around for a while. We've got now the compute power to efficiently implement neural networks. And now we've got the data to train those. And so the networks are getting deployed widely across multiple applications. And it is driving change in the compute architecture. So we've been using CPUs and GPUs to do a lot of these neural network computations. And those are doing a great job and are the dominant solution out there in the market. But to try to get more efficiency, many companies are developing their own custom architectures that are specifically tailored to a network that they're using. So everyone has their own slightly better way to solve that neural network problem. And we're seeing these new architectures being deployed. And of course, these new architectures are going to require custom memory solutions. So specifically, as we look at the training, the data sets continue to grow at an exponential rate, even going to be approaching a trillion parameters. So this clearly is putting pressure on both the memory bandwidth and the processing. So there's research going on how to try to efficiently use these data sets. And as an example, things like sparsity, where in a neural network you're multiplying by weight. So in a network where you have a 0 or something close to 0, you can gain some efficiencies by multiplying by 0. That saves processing and saves power and saves memory. But at the same time, these you can, based on just the raw size of these data sets, that the memory bandwidth is continuing to get pressured to grow. And there's current we're going to look at those in just a second, but there's current standards around high bandwidth memory, and those standards are continuing to evolve, and we're seeing even higher throughput type memories. So I went just from a very kind of high level down to much detail. So sorry for kind of switching gears. But let's just dive in and start looking at some of these memory systems are. And again, I'm not going to go through all the data. You can take a snapshot or download the presentation later to go through this in more detail. But as you can see across the top, we have a number of different memory solutions. And up until fairly recently, the only memory available really was DDR, right? It's still being used across, across many applications, especially in the server type application. So it's a good, well-known, well-understood memory, a good price point. But you can see it topped out at about 3.2 gigabits per second, and that just was not enough bandwidth to start to address some of these AI applications. And so that kind of gave rise to HBM memory that came out back around 2015 timeframe. And so HBM was basically using the same DRAM technology, only stacking it in a 3D fashion. So you're taking roughly the same technology, you're stacking it on top of each other, and you're increasing the interface. And you can see the interfaces there are going from around 64 bits with DDR all the way up to 1,024 bits with HBM. So you're getting this kind of wide and slow concept. And so the wide and slow concept gives you the bandwidth you need. It gives you the good power efficiency. But of course, now you've got to deal with 1,000 signals. And so we're going to look at that in a little more detail. Another memory solution that also kind of moved away from, or is in addition to the graphics market, I should say, is GDDR6. So you can see from a per pin rate, GDDR6 is 16 gigabits per second. Again, so that's the actually highest pin throughput, per pin throughput of any of the memory solutions. But even at that speed, it's okay for training, but we're seeing other applications like AI inference for GDDR6. And GDDR6 advantage is that these are more of your traditional style, put it down on the PCB and not have to deal with the 2.5D infrastructure. And other memories we're seeing in AI is LPDDR. You can see LPDDR is LPDDR5 up to 6.4. These are good memories, especially if you're doing AI at the edge of the network, where you're running somewhere in the neighborhood of less than 100 gigabytes per second. LPDDR could be a good solution. So these are the choices, and we're talking to customers at Rambus every day, trying to make the trade-offs about what's the best memory for the application that they're trying to solve in the network. Okay, so let's just drill down a little bit and look at HBM and GDDR6. And so you could see on the GDDR6, from an application standpoint, it's starting to find homes in AI inference. Of course, graphics is where it's been always, but also automotive is another good application for GDDR6. Bandwidth starting in the in the 300 to 500 gigabytes range is very good for like an ADAS type application. And GDDR6 from a reliability standpoint is a good solution because, again, as I mentioned, it's the down on the PCB kind of interface, so much more traditional manufacturing model. But for applications where you need even more bandwidth, HBM has become the memory of choice. And so for AI training, high performance computing, HBM is even being used in the network for like NIC cards as well. And so let me let's take a little bit more peek into that 2.5D architecture. So now we're looking at like a cross section of an HBM on the bottom right hand side, and you can see the if we look, you've got the 3D memory that's stacked up. So this is a 3D. These are slices of DRAM that are stacked up in a 3D fashion with through silicon vias, and then that's connected to a processor, and you've got all these signals running. And the only way to really route these signals today, the technology available, is through a silicon interposer. So you can see that the processor connects through a silicon interposer, and then this all sits on a substrate, more laminate substrate, and then this goes on a PCB. And so this looks like into a package. So this is a very well-contained system. Oops, excuse me. A very well-contained system, and we'll talk a little bit about some of the challenges of doing the 3D. One of the things you have to be very careful when you're doing this interposer is you really have to look at this particular channel. Right? So you've got all these thousands of signals running through the interposer, so you have to look at how long these signals can be. You have to look at the characteristics on the interposer, like how thick these signals are. You got to worry about things like crosstalk, ground planes. And so these are all new challenges that engineers didn't really have to deal with in the past. And so this is, one of the kind of new things that customers are looking for help, companies like Rambus to design. How do you actually design these interposers and the packaging systems? And one of the things we have to do a lot of work around we have to get these channels, we have to simulate them, as part of the design. So we have to ensure that this is going to work properly. So I may have covered some of these. I'll just go over them. So one of the advantages, as we talked about, is very high bandwidth. You've got very high power efficiency because you're running wide and slow. The proximity to the processor memory, so you have some kind of near, not quite cache, but you kind of have near memory to the CPU. And of course, this is a very small footprint. You get all this processing power, all this DRAM in a very small package. And some of the challenges, you've got this new interposer technology, so there's a cost associated with that. And it's a relatively new manufacturing process. And so all the companies, although it's well understood in some sense, the volumes are still growing, and it's a relatively new technology. And so there's some additional complexity. So you get all these advantages, but you've got some complexity to deal with in the 2.5/3D infrastructure. So if we look at the Rambus solution, there's you can see on the right, this is a memory subsystem that we offer. So the complete memory subsystem for HBM includes the HBM2E memory controller and the HBM2 PHY. So the controller talks to the ASIC. This is all part of the ASIC. It talks to the ASIC. This could be through an AMBA or some kind of a bus structure. And then the physical layer talks to the DRAM. And one of the things that Rambus offers to the customers is extensive production experience. Like I said, this is a relatively new technology from 2.5D structure. So having been producing these things now for since like 2016 gives us a lot of experience on some of the challenges you're going to face in terms of developing these HBM systems. We provide a hardened timing closed PHY, which is also a nice advantage. So you can drop this into your ASIC in a pretty clean manner. And then we have the interposer and package reference design. So every system has a little bit different requirements. And so having a good starting point on that interposer really gives the designers of these systems a jump start. And we have a really nice development environment called LabStation that allows you to run traffic data to bring up the PHY independent of the controller. And it's a very powerful system to bring up and debugging. From a performance standpoint, the Rambus PHY runs at 3.6 gigabits per second, and that gives you 460 gigabytes bytes per second of total bandwidth. So again, very high performance. This is about 12% higher than the previous 3.2 gig that's out there on the market. Again, trying to push the bandwidth, and we even did a press release last year that this will run up to 4 gigabits per second. So that'll give plenty of margin as you're designing the system. I'll take a minute to just talk about the memory controller. And so you can see one of the main things you want out of your controller is good memory efficiency. So you've got all this DRAM out there, but you want to use it as efficiently as possible. And the other thing is you want it to connect up to your system efficiently. So the controller is very configurable. You see those lighter blue boxes on the left-hand side. Those are, we can customize those blocks to talk directly to your SoC and to your ASIC. So whether you have a AXI interface or we have a native interface that's very efficient, you have multi-ported interfaces into the controller. And then other blocks like read, modify, write, or ECC. In some cases, you'll want to have error correction. and those are all customizable. And then along the bottom, you see we have again more memory test capability, and this is always a very useful feature as you're developing your product, to be able to get in there and look at the memory and analyze what's going on. And then the PHY and controller in this case are validated together. We use a DFI interface, but that's usually hidden from the customer if you buy our whole memory subsystem. So again, we not only validate the PHY and controller, we build test chips as well. So we've done about, for HBM, I think we've done 4 or 5 test chips now that show for different process nodes that validate that silicon. So again, very good confidence that you get a subsystem that's been validated and tested and widely deployed in the marketplace. Let's see, any other features here? Yeah, so that's it. So just let me summarize a bit. So the, again, the amount of data is driving the need for, the amount of data is driving the need for faster and faster processing and memory interfaces. And so HBM really a good memory system to address the needs for AI training and it's continuing to grow. So today it's at 3.6 gigabits. We expect that there's been some recent announcements that the next generation is going to come out to continue to even maybe double or even greater than double the speed of that memory interface. Rambus has a ton of experience. It's been obviously memories in our name. So we've been working on HBM for a long time and really helping customers to decide what's the best memory system that's right for them, and looking at all the different trade-offs in the memory. So that's a quick summary of the presentation. Now we can take questions if there's time.
Hi, okay. That was a great presentation. I loved it, clear and succinct. So I'm going to just kind of start off with some questions that we're getting from the audience. Kind of a quick, kind of like an overview-esque question is, what does the 2E stand for in HBM2?
So the first technology was just called HBM, and HBM. Then the second iteration of that was just HBM2E. It was really extended. I think JEDEC used that as kind of extended or extension. So first generation was 2 gigabits per second, and then HBM2E came out at up to 3.2 gigabits per second. So it's very similar. They're not 100% compatible, but very similar.
And then the next kind of question, for your memory subsystem, how do you deliver the IP? Is it synthesizable like RTL? Is it like a hard macro? How does kind of Rambus help their customers integrate the controllers?
Yeah, so the answer is both. So the PHY is delivered as a hardened macro. When you have these physical layers, they have to run very fast, and they're very tightly coupled to the process node. So if the specific process node we have to develop the PHY for. The controller piece is delivered as synthesizable RTL. So that is, but we validate that entire subsystem and deliver it. So we deliver the controller as RTL, we deliver the PHY as hardened, but that system's validated as one memory subsystem.
Okay.
Yeah, one of the advantages of delivering the PHY, hardened, as I mentioned, is that we do the complete timing closure on that. So you can drop that in. The memory PHY includes the decap. It includes all the I/O. There's really nothing that the customer has to do from that standpoint. So that's a very efficient way to get them, to get through their ASIC design quickly.
So to kind of touch on that too, like you guys do like EER, ER/IR timing or EMIR timing, all that comes signed off as well.
That's right. That's right.
Oh wow. Okay.
Yeah, we do the test chips. In our test chips, we validate the functionality of that, but the customer has to do. They have to do some of the. I mean, it's their ASIC, right? So they still have to do that work.
So kind of also a little bit, you briefly had on your slide something about lane repair. can you kind of touch a little bit more on that?
Yeah, yeah, I did skip over that. Thanks for bringing that back. Lane repair. So you have all these you have multiple channels on HBM, and with each channel you have redundant bits because you've got so many bits that are running on data, running data through. So if for whatever reason, as you're going through your memory, a bit gets corrupted, you can remap that data line to the redundant bit in that, and so that gives you some ability to do real-time repair.
Okay. And then a kind of another question is what kind of like a design for X that does Rambus kind of offer as far as like what DFT offerings do you guys have, MBIS, Visor sort of interfaces, what scan chain hookups do you guys offer?
Right. Yeah. So all these PHYs and controller come with a design for test interface that we describe in our data sheet. So it's pretty detailed, and in some cases we'll even customize it for the customer. But yeah, we have the fault coverage and DFT is built right in. So when you do your ASIC, it can be integrated again pretty easily, and most customers are okay with our standard DFT interface.
Okay. And then one from the audience. So can you kind of discuss a little bit more about what does Rambus see as far as upcoming innovations for HBM? What does the roadmap kind of look like for that?
Yeah, I mean, we can't really necessarily speak for JEDEC, but I think it's already been out there that it's been published that HBM3 is the next generation standard that's coming HBM, and then the same thing with GDDR. There'll be a next. You're currently at GDDR6, so you can guess what the next number will be for GDDR. I think that one's been published yet. But anyway, HBM3, that's information that's out there right now is talking about 6.4 gigabits per second, and so that's effectively doubling the data rate. I think the interface will be the type of technology will be very similar. There are some other changes that are thinking about power efficiency on the interface. Yeah, it's taking the extension of the technology. And so when you're going up to those speeds of 6.4, now the interposer designs are going to change a little bit. So right now, typically you'll see interposer designs with 2 or 3 routing layers. As you're going faster, you may need additional routing layers. They're all passive components. There's no components. It's just interconnects on the interposer. And now maybe looking at doing potentially some other components on the interposer to help mitigate some of the effects of these signal integrity effects of crosstalk or insertion loss and things like that.
So I guess my next kind of question comes down to area. So do you guys have kind of a quote for how big these controllers are, and let's say like TSMC 7 nanometer or something like that? And on top of that, how do you when you talk to a customer kind of balance the area of, let's say, one of those memory controllers versus like a DDR memory controller versus a G6 DDR controller?
So from the physical layer, the DRAM itself, especially in HBM, dictates the area, at least from the beachfront. So you need to get a very nice, one of the ways you get good signal integrity is for your ASIC PHY interface to match the DRAM PHY interfaces. So that there's a specific spec, and so that beachfront is defined, and you want to get nice, straight, clean traces between the DRAM and the SoC. So that's pretty fixed for everybody. As far as the controller goes, and then of course you got to go deep into the chip, and that's also the number. All those bumps are also defined. So that kind of square rectangle shape is really effectively defined by the DRAM spec for the most part. As we get into the controller though, then the area does change a lot depending on what you want to do in terms of if you have ECC, what are your buffer sizes, how many queues, things like that. And that greatly varies from customer to customer. So it's hard to quote a size. I mean, the controller is relatively small overall if you think about the area in 7 nanometer. But again, the thing that varies the controller is the amount of memory you want on that controller in terms of buffer.
So Okay, so kind of you touched a little bit on G6 DDR, and we've mainly been discussing HBM. But with the massive bandwidth that we see with HBM, how do you actually see kind of G6 DDR ever playing out in the AI machine learning space? Because it might as well, if it almost looks like it makes more sense to kind of just have the HBM interface.
Yeah, if you could afford the HBM interface, then yeah, that's true. But the cost is still, and the complexity is still there, right? Doing these 2.5D manufacturing process, there's a number of fabs, foundries that are trying to make this and have made this turnkey, which is nice, but there's a cost to that. So if you really don't need all that extra bandwidth, then GDDR is a good alternative. I mentioned that if you so training these models is complex. If you have a large model, depending on your processor and bandwidth, it could take days or even weeks to train these models. But once they're trained, then they can kind of push them out to the network, and that's where you get into the AI inference. So if I needed terabits of processing to train the model, once I have a model trained, I may only need hundreds of gigabits to actually run that model. And in that case, something like GDDR, 3 or 4 GDDR DRAM can run that very efficiently, and again without having to go through the whole 2.5D manufacturing. So we are seeing customers who are doing AI inference, whether in the network or at the edges of the network. GDDR looks like a nice solution.
So kind of for also if we're going to talk a little bit more about price, for like the aspiring SoC designer, the startup CEOs that we have here, what does the price to customer kind of look like, at least relatively speaking, in as much detail as you can give, for HBM2E versus DDR4 versus HBM versus G6 DDR?
Yeah, so just kind of relatively speaking, if you're talking about GDDR versus HBM, it could be as much 4x more for HBM. For if you pick a bandwidth, say pick 500 or 300 gigabytes, so you'll see somewhere in the neighborhood of 4x more for. And I think GDDR and DDR is still the cheapest. I'm not sure exactly the factor for those. And I think if you think DDR is the cheapest, kind of GDDR and LPDDR are similar, and then HBM is the most expensive. So just without giving any specific numbers.
Okay, and I think that kind of wraps up our Q&A. We're starting to run a little bit low on time. And I just wanted to say before we kind of all bug out for like our little break, you'll be here for the breakout sessions, right? Starting
I will be here.
Yes.
Correct.
So
yeah.
I was going to say, Frank,
talk to you then, yeah.
Frank will be here. He'll be able to answer kind of your more in-depth questions for memory solutions, some that kind of require a little bit more of a personal touch. I know there was some in the chat that we didn't necessarily get into. There's one that kind of discusses the roadmap of what memory looks like versus having external memory versus in-memory compute, and what does that look like. So please sign up for the breakout sessions. Frank is an expert here. He will debate all these questions with you. And yeah, do you have any parting words for regarding memory, life advice, whatever it may be for us?
No, first of all, thanks for listening in. And like I said, I will be available to chat, in a little bit more detail for, I guess we got about an hour later in the day. So yeah, I look forward to talking with you. So, but thank you, and I appreciate you taking the time to tune in.